All right, thank you everybody for having myself and my colleague Stephen Oberlin here to talk to you about maximizing your installation. I'm the technical sales manager with Owens Corning, and Stephen is an architect and project lead with Republic. Today's quick agenda is going to be on exterior insulation design considerations, carbon impacts of insulation on the building envelope, and then we're going to establish some clear building performance targets and talk about key factors impacting the effectiveness of your insulation. So let's dig right into this last one of the day. Exterior insulation design considerations. So something to think about over the last little bit, we've seen the building code change significantly. Back in the day, you want an R42 wall, you just put the insulation in the wall and it'd be considered done. That's it. Or for example, R22 bat in the wall gets you put that in the wall, it's an R22 wall. Well, after NECB 2015 was adopted, we started to talk about more effective R values, which I'm going to talk about the definition of that on the next slide. So we saw our insulation values for the wall cut, or the amount that is actually showing now cut almost in half to R26, because we started to take into consideration the studs, because the studs are not R22, the studs are probably R6 or even less if it's steel. Then we also have the NECB 2020, which just came in effect, and most provinces have already adopted this as well. Oh, Manitoba did for sure. And now we're looking at the effective R value for the whole wall assembly, and now we're looking at different junctions as well too. So not just the studs, but now around the windows, the top of the wall, the bottom of the wall. So that's why now the overall value of insulation for that wall now went down a little further. So we have a couple different types, and you may have heard these terms before. I'd just like to give a little bit of a refresher. So we have what we refer to as nominal R value, or sorry, first let's talk about the insulation R value, which is just the sum of the insulation, typically labeled on the bag. Then we have what they call the nominal R value of the wall. So we put an R22 bat in the wall, that becomes R22 wall, right? So that's a nominal R value. Then the effective R value. So now we're taking into consideration those studs as well and any of those junction areas. So because the studs do not have the same R value as the insulation, they tend to contribute to something called thermal bridging. Now, thermal bridging is something that occurs within a component that it has a relatively higher thermal conductivity, bypasses the thermal insulation. So, for example, the heat would go through the wood versus, or the steel framing versus the insulation. So if you took a picture of a house, it would look like this. Or if you're in a beautiful Winnipeg and it is -30 and you drive by a house and it doesn't have any exterior insulation on it, you probably can see all the lines of all the studs. If it's 2 stories, you can probably even see the floor lines as well, where the heat is leaving the building, losing energy. So the solution that everybody came up with was to cover it up. Like, let's have exterior insulation on the building, because then we're covering those junctions or those areas where heat could bypass. So now we're able to mitigate that, reducing the operational energy that the house has to use. So when we're looking at this, the key thing, when we start looking at exterior insulation, the key thing is your cladding attachment performance. So if we look at a standard wall, we have an R20 bat in the wall. Well, the question would be is, what is the effective thermal resistance of an R19 or R20 bat in a 2x6 stud wall? Well, you're going to lose about approximately 20% or to 20 to 30% of that insulation value. And that's due to the fact that the wall or the wood studs are about 20% to 30% of the wall. If it's steel studs, well, steel studs have even less more conductivity for heat than wood would have. So you have a potential to lose about 50% of that R value in the wall. So that R20 wall looked like a great wall, but then it turns out to be an effective R10, right? So that's kind of where we were looking at when it comes to the effectiveness of insulation. And I'm going to come back to that, because you're going to start thinking like, why do I even put any cavity insulation in the wall? Well, we'll talk about that in a second. Then we started to go to exterior wall insulation, and we went to a girt type system. As you can see, these lines right here will show a girt system. There's no, you know, insulated clip or anything like that. It's just steel on steel. Well, this sometimes had the ability to conduct or continue the thermal bridging. So you potentially will see 50% of that R value on the exterior wall deteriorate as well. So you might have put 5 inches of exterior insulation, but you're probably only getting approximately R value for about 2.5, right? But then we saw the evolution of the clip, and then we have the isolated clips here with a little bit of separation between the wall, providing less conductivity. Fiberglass clips, other types of clips like that to reduce the conductivity of the thermal bridging, and that allowed a 15% reduction in the insulation's effectiveness. So, okay, we're doing a lot better. Now we're getting more out of our insulation on the exterior. We can even go to a little bit of a thinner wall and still be able to get the same performance. And then we can even go potentially to an even thinner wall if we use the direct attachment approach. The direct attachment approach is using long screws to go through the wall into the studs. Now, there's considerations to be held when it comes to that, because one, you definitely have a more effective wall, but then your cladding weight now starts to come into consideration, right? So now again, I'm going to go back to the question of, if we're looking at the steel stud and it says approximately 50% of that wall, or you're going to lose 50% of the insulation, why do we do that? Why don't we just put everything on the exterior? Well, the reality is of this is you can see sometimes you don't always need an extremely thick wall, because if you take a look at these two assemblies, they both have a clear field value of R30.4, both overall 20.1, but we only use 5 inches of, say, mineral wool on the exterior. Now, it's going to vary between the types of insulation. Every insulation does have its place. So you're going to see me talk more about fiberglass and mineral wool, because those are common ones that I seem to see more on the market. But all the installations are available. XPS is another one that we see commonly as well. But it's just to show the difference between having a full exterior wall versus having some in the exterior, because now not only are you able to make your wall a little thinner, but there's a cost savings to that. There's also one more factor that I'm going to discuss when it comes to making your wall a little thinner, and that would be the carbon impacts of the insulation on the building envelope. Because when we just discussed, we discussed thermal bridging and using exterior wall insulation, and we decided to cover it up. Well, that's going to reduce the operational carbon that the building produces, because now the building is going to use less energy, should have a smaller now mechanical system in there, would potentially use less energy that way. And because of the exterior insulation, because of better insulated, and air tightness is key too. Talk a little bit about that towards the end as Stephen takes over. But operational carbon, now we've decided we've got that mitigation happening. But what about the embodied carbon piece? This is something that's coming up. It's going to be in the 2030 code as well. What do we do to reduce that impact? So we take a look at this chart, and these charts came out of the Material Carbon Emissions Guide from the city of Nelson. They were one of the people on the forefront putting out this information, and they talk about different types of boards. Now, these are all industry standards, and I know there's a lot of numbers on here, so it might be challenging to see, but you can see it's just industry standards, and a lot of these numbers have gaps in between. They just put the average, but some boards will be a little bit lower, some boards will be a little bit higher. But I'm just going to talk about the industry overall. One thing to note, you can see right here, when it comes to foam's got a pretty high carbon emissions, or basically about 715 kilograms of carbon emissions per about 100 square meters. That's for your rigid boards. We can take a look at mineral, a little bit better for sure. At 473, again, industry average. Some boards are less, some boards are more. And then finally, we look at boards like wood fiber, where they actually are carbon sequestering. Now, there's a lot of carbon sequestering products out there as well, too. So if you want to reduce the overall assembly, you can use some of those as well. That will continue to reduce the amount of embodied carbon in your overall assembly. That's just on the rigid board side. So that's the exterior insulation side. We take a closer look at the cavity wall insulation, and we can see mineral wool again is up there around 608 kilograms. Then we look at wood bats. So wood bats are on 296, and then we see fiberglass down there at 154. So you can see, depending on your insulation choices, can really affect the amount of embodied carbon in the wall, because potentially can be about 4 times more depending on which products you're looking at. Now, I took a just an example out here. Please ignore the cladding attachments. The measurements and calculations on here are only related in reference to that City of Nelson Guides material carbon calculations. So I use their numbers to calculate what an R10 wall would look like with R24 insulation. This is just, and I have to always be clear, this is just the insulation only. Okay, so not ignore the cladding attachments, because if you start adding that in, that's going to increase the amount of carbon in the embodied carbon in the overall assembly. So we can see XPS, what XPS in fiberglass does. We can see what XPS in mineral oil does, pretty much the highest one on the sheet. And then if we go, or in these examples, then if we go mineral oil, all mineral oil, and then we go to fiberglass and mineral oil. So you can see the significant difference by just changing some of the components can reduce the overall embodied carbon of the wall. And just to give you kind of a rough idea of where what these examples kind of reference. So if you're about 1,254 kilogram or carbon emissions, that's the equivalent to about 534 liters of gas. So if you're at about 2,154, like the all mineral wall, you're at about 918 liters of gasoline. So that's how much fuel potentially or carbon you're emitting based on these types of assemblies over this 1,000 square feet or 1,000 or 100 square meters. Okay. And then the big thing though, and I've gone through all the carbon, and like I mentioned before, there's a lot of carbon sequestering installations out there. But this is a report that was just put out. I was on a presentation with NEMA, and they shared this information done by a consulting firm in the States called ICF. And they were talking about the carbon payback analysis for thermal insulation in residential and commercial new construction. So there's a memo that they brought out, and from their testing and results, they were able to show that basically most installations, and this kind of relates to most bad installations out there, typically the embodied carbon payback is under a year for those. And then in commercial buildings, if the total is under 10 kilograms, usually under a year for so. Typically, you'll only see more in foam products. But that being said, it's only about another year before they pay off. And I say only, I mean, we all should be looking after the environment, doing whatever we can to reduce the amount of carbon that's being put into the environment. So whatever differences you can change, take a look at that. But we also have to look at, the total overall cost of the building over the lifetime as well. So we have to see where the testing is on certain products to make sure that they all perform for the life of the building. So we're not constantly replacing them, even though they're better for the environment, right? Unless that makes them better for the environment as well. So just looking at a couple guides that we have here. So there's a resource guide for embodied carbon. There's the City of Nelson one that I mentioned. There's a low carbon solutions for multi-unit residential that was just released in November. CLF, which stands for Carbon Leadership Forum. There's a number of them in different areas of the country. British Columbia actually has a guide, and it has calculations or different amounts for these particular installations as well. One of the last things I want to leave you with is the product transparency. So make sure when you're looking at EPDs, that's where we're getting a lot of this information from. There's 3 different types. There's industry ones, like I was mentioning before, those numbers that I was showing. There's also manufacturer specific ones, and then there's product plant manufacturer ones. So they would tell you the product that was made in a specific plant, what the calculation was. There's also summaries available and health product declarations. So take a look at all the information. Don't just look at the industry standard. Look at all the different companies and see what they're doing as far as making their products as clean and as less impactful to the environment as possible. And finally, airtightness. It's all about airtightness too. It's all about the details, whether you decide to go all exterior or whether you decide to go with a split wall or hybrid wall assembly. Both of them, the key thing is considering the details. So airtightness, insulation, that's the way we work to maximize our insulation. Now I'm going to pass this off to Stephen, who's going to talk about building performance targets and key factors impacting the effectiveness of your insulation. Steve, take it away.
So I guess my goal today is really to talk about how Andrew doesn't need to sell you more insulation to make sure that it's effective. What? We do need some insulation, but only to a point. Um, so again, I just like thank Sustainable Building Manitoba for the opportunity to present here today. Hopefully, this presentation is going to provide some insight into the design processes here at Republic and things that we've found to be particularly effective in terms of providing value to our clients and how we're able to work from project goals and how those shape the building design to suit the functional needs of meeting either their performance mandates, the functional requirements of the building, and really looking at maximizing the effectiveness of what we're able to provide um, value wise in terms of both material efficiency and fiscal efficiency in the building envelope designs that well, man, the building envelope designs that we put together. I'm going to focus the majority of my presentation today, so it's not wanting to go on a series of buildings that we've done. I had the ability or the rare ability to look at them right across Canada. So this all started as a cross Canada feasibility assessment for net zero or net zero ready multifamily buildings. We looked at 5 different archetypes. So we had a 6 unit, a 12 unit apartment, a 4 unit row house, a semi-detached house, and a single family dwelling that we've looked at 7 different climatic locations across the country. And it's to be rolled out at 11 different sites across the country. Um, Today, I'll focus on the discussion around the 6 unit apartments, the items that we applied, the design philosophies, and the lessons that we've learned from these projects to date. I will note the effective values of the roof assembly are R86. It's about a R95 nominal. It's blown in cellulose. The exterior walls are effective R32. They're a nominal R46. They're a hybrid wall. So it's a 2x6 wood stud cavity plus 6 inches of through fastened exterior mineral fiber insulation. Our floors on grade also have a effective value of approximately R17 and a half with a nominal value of R20. I think this project, I like to focus on it because it provided us a unique opportunity to get a deep understanding of what the climatic and location or like the environmental factors are and how they really can drive how we tune our wall assemblies, our roof assemblies, and just the overall performance of the building to specific regions and specific sites. Uh, the And I think in doing so, this is really coming from a place of understanding where the performance or what the performance goals are. And I think this is the number one thing in terms of maximizing your building assemblies and maximizing your insulation is trying to understand what the targets are. Is it to reduce thermal demand? Is it to provide cost savings? Are we looking at return on investment? Are we looking at overall decarbonization targets? Are we looking at electrification? And I think really understanding what those targets are helps us understand where we need to go in terms of tuning the building assemblies to a specific site, a specific location, and really maximizing the value that we're able to provide with the buildings to our clients. Um, I'll say these projects themselves started as net zero energy studies with a bit of a greenhouse gas intensity analysis that let the project explore what it meant to be net zero ready, and then further understanding what that meant in relation to our clients' mandates. Um, I'll say this was largely based on the organizational mandates that were coming from our client, but it provided the project team an opportunity to work with the client in establishing a specific interpretation of what this meant to them and how we were able to deliver upon it. In the end, we concluded that to be net zero energy or net zero energy ready required the ability to produce the net annual amount of energy consumed by the building on the building itself. So this meant either building integrated photovoltaics or rooftop mounted photovoltaic panels, providing the amount of energy that limited the overall amount of energy we were able to consume. So we established the rough geometry of the building, worked on tuning the roof angle in location to the solar orientation, worked with a solar consultant in understanding the net annual availability of solar energy that could be produced, and kind of worked backwards, where we set that as our overall annual building energy performance target, and tuned our building assemblies to be able to hit this target and make sure that we had a bit of a buffer in terms of 2 to 5% of additional net annual production versus our projected net annual usage. Oops, sorry. And I will say that both myself and the team here are firm believers that the building of a building envelope first approach to design. And really, this entails modeling early, modeling often, and really using your instincts as well as historical performance calculations to set a baseline, but really building upon it to provide the value to our clients. This provides the opportunity to right size your mechanical systems to the project. And I think this is where, unfortunately, we typically don't fully understand all the trickle down impacts of doing so. I think, in terms of being able to really discuss return on investment and how much benefit we can have by focusing on sizing the building envelope first, reducing thermal demand, and then scaling mechanical systems to suit what we're able to do at that point. These here are just kind of where we start, or where we started on this specific project, which is looking at a series of energy conservation measures and a comparative analysis that we worked on in conjunction with our sustainability consultant or modeling consultant, AME. These specific set of ECM outputs are for a building site that was slated for the pilot project in Edmonton, Alberta. This was done right at the outset of the preliminary design phase and prior to making any major decisions regarding building assemblies, mechanical systems, and so forth. As you can see here, we have different inputs and how they lead to different outputs. So this is really just automating the process of looking at U value 0.18 on a window, how that combines with the effective R value of a wall assembly and the heat source or the ventilation source within it to look at either um, the thermal energy demand intensity, the mechanical energy usage intensity, total energy usage, or the greenhouse gas impacts, or a bit of what would now be considered, I guess, a life cycle carbon analysis. Um, and then looking at the incremental cost impacts to the project. So we had a bunch of different factors that we could change the input variables on and get a better understanding of what the output results were at a very high level, and then use this as a baseline to understand how to further tune the building assemblies and the building envelope to really be what we needed for this project. And as you can see, these are kind of sorted by different targets or different performance metrics. So one thing that really surprised us here, and this is due to the grid intensity factor in Alberta being very high, they've got a lot of coal feeding their grid. So the grid intensity factor played a major part in driving what you see as the lowest greenhouse gas emissions, the top ECM graph on this slide. And what's I think probably surprised the design team the most is the fact that it was telling us that an air source heat pump with a high efficiency gas furnace as a backup or auxiliary heat source actually was going to provide us with the lowest greenhouse gas impact on this project, including the operational carbon um, to operate this building. And I think this was a bit of an anomaly. I think there's really three jurisdictions within all of Canada that we looked at. So Nova Scotia, um, with Nova Scotia, New Brunswick, and Alberta, potentially also Saskatchewan, that had a grid intensity factor that really didn't show the value of what electrification can do. This changed a little bit when we looked at simulating this out over like a 30-year projected time horizon that took a look at both the projected cost increases of electrical as well as natural gas costs, and as also how the grid intensity factor was slated to change over time to hit our 2030, 2050 energy goals as they related to the federal government mandates. Sorry, that's going maybe a little deep here. Um, what's the next slide? So this is a bit more of a breakdown. So if you look at the annual energy usage or the proposed sort of pie chart we have here, you can see the overall reduction from our reference model. In this case, our reference model was the standard reference model you would do as a baseline tier one model building. The largest portion of this energy pie is really related to domestic hot water. And we feel like, unfortunately, this is a bit of maybe a hiccup within the compliance modeling processes required for the National Energy Code. Um, but again, we're working within the constraints of the system that we're sort of operating within, which is the NECB. But we've really taken the amount of space heating and space cooling energy we can by tuning the building envelope in this case to to really find almost that point of diminishing returns in terms of how much insulation do you really get the value of in your roof, how much insulation can you um, provide on the wall, and really make sure that you're getting the full benefit of it. So we did wall simulations where we looked at anywhere from 2 inches of outboard insulation to 12 inches of outboard insulation, and try to really understand where made the most sense in terms of thermal energy demand um, for the building and how that was shaped by the exterior insulation. And then if we look at the next slide here, I think what I really want to aim on is this is a snapshot from a sensitivity analysis or comparative analysis of different factors based on our modeling. And it's really, as you can see here, there's an outsized impact of infiltration rate. So that specifically speaks to air tightness, air sealing, and ensuring we've got a control over what air enters and leaves the building. Um, Based on the development and rollout of this building typology across multiple climate zones and locations in Canada, we found that this has really been the single largest factor in reduction to thermal energy demand intensity, and that's really focusing on infiltration rate. This leads us to a series of both material and detailed design choices to really ensure that this is executable and we're able to achieve uh, the air infiltration rates that we're using in our models on site. And based on the performance we're seeing from what's been tested on site to date, we're quite conservative in our estimates in terms of an ACH target of 1.5, ACH of 50 Pascal. So it's a fairly moderate target considering passive house is zero 0.6. We found that we probably could have gone to an ACH target of 1.0 and really still reap some benefits from that. But there was a bit of a hesitation to make sure that we weren't setting ourselves up for failure by being too aggressive. So again, when we're talking about what I like to refer to as like the levers of thermal performance, when we talk about building envelope, really there's the insulation values from all these different assemblies. And once you get them to a certain point, which is kind of somewhere around tier two of the energy code, if we're looking at it from sort of like a more prescriptive standpoint, that sets you up where you really have an outsized impact of controlling air leakage and dialing in that infiltration number when it comes down to understanding the thermal performance and thermal energy demand based on like the building assembly. I mean, windows and doors are something that definitely can't be forgotten, and making sure that they're installed in such a manner that they're airtight, they're resilient, and they will be durable throughout their projected lifespan. But Again, coming back to air sealing, again, looking at windows and doors and managing these penetrations is really key to ensuring that the insulation that you're putting on your building is really providing its full value. And then the other thing when we talk about building to suit is there's a number of factors specific to each project which will outweigh the perfect wall or other rules that are discussed in the the building science world. Um, And this is a bit of a philosophy that came from the client in approaching these projects as well. They wanted to ensure constructability above all else, as well as looking at what we can do with readily available materials and trades. Because the biggest thing to them was this wasn't seen as a one off building, which typically most of the buildings will work on as an architect will be. But this was seen to be something that they wanted to be massively scalable and really roll this out in a number of locations across Canada. So we were trying to stay away from the bleeding edge of new building materials and systems, and really leveraging the availability of materials that were already out there in the market. Maybe looking at exploring how our details could really support maximizing the overall efficiency and performance of um, more generic or more run of the mill building materials. Again, I just want to note here that if a detail or material cannot be executed effectively on a construction site, it's going to be very difficult to achieve the model performance of the building assemblies. And this is especially true at scale. Just for an example, our pilot project is actually a set of 6 buildings being rolled out in Edmonton. So there was no one specific building that we got to test from this on. So that led us to being fairly conservative in our estimates and making sure that the assemblies that we provided were very um, both risk averse and durable in terms of their expected performance. Um, I mean, this is something that kind of gets us into a weird bind where we find that sometimes adding more insulation is really just a net negative in terms of hitting other sustainability goals. Because sustainability, unfortunately, is not just thermal performance. We need to look at greenhouse gas intensity and carbon footprint. Um, and I think this specific site in Edmonton that I was first discussing was um, we were seeing a very outsized impact on operational energy savings just because of how dirty the grid was there. Whereas when we took that and shifted that to a province like Quebec, which has, I think, a fairly similar grid link up to what we have here in Manitoba in terms of um, its overall global warming potential per kilowatt hour or gigajoule. I'm not exactly sure the best way to measure that, but we found that fortunately, sometimes looking at the qualitative impacts on thermal performance or energy performance put blinders on a little bit in terms of the global warming potential of the materials chosen for the building assemblies. And again, this is pretty similar to, I think, what Andrew had shown in his slides, but this is a bit of a comparative analysis of the global warming potential as measured in kilograms of CO2 equivalent per RSI. I should state this is at 1 meter squared, not 100 meters squared. So it's a little bit different than what Andrew had presented. But you could see that cellulose based insulations, fiberglass based insulations, kind of are your most effective in terms of greenhouse gas reduction. The thing that I guess we need to consider is the fact that those aren't independent. They come along with studs and sheathing and a bunch of other components that do drive up the overall um, global warming potential of the assembly. But we found that the hybrid walls with insulating that cavity are a very effective means of insulating a building in relation to the global warming potential associated with them. So here, this is just a bit of a breakdown in terms of key factors affecting impacting the effectiveness of your insulation. So really, it's what is the climate zone we're working within? What is the location? Are there specific conditions? Is this a place where we get hundreds of millimeters of rain on a monthly basis, or is it somewhere that is fairly dry? Because as that's something I'll get to later in this presentation, if you're making sure that your insulation stays dry, you're really gaining the full benefit of its effective R value. Um, so I think here, again, insulation, which insulations are we choosing? Are they vapor opening? Or are they vapor closed? What's the overall drying potential of that wall? Are we ensuring that we've got primary, secondary air barriers? Because I think it's not necessarily a question of if something will fail, when something will fail, and making sure that there's redundancy built into the assemblies to ensure long-term durability. So just going to jump through this. So again, sort of critical considerations or key factors that we've found when we're looking at putting together the wall assemblies on these buildings is that air infiltration is an outsized factor. There's a bit of a caveat here where that's starting at a baseline of already meeting the prescriptive minimums for the energy code. The next thing here is moisture management. So if you have, it almost doesn't matter what insulation type it is, if it gets wet, you're never going to get the full value of its anticipated uh, thermal thermal resistance. So another thing here, which I think is maybe lesser modeled or lesser factored, is wind washing and settlement. So especially on loose fill or like a dense pack style insulation, making sure that that material is understood in terms of how it will settle, how it could potentially be moved by the winds that will move through an attic space as the building sort of breathes and lives, as well as really understanding thermal bridging. Because I think Andrew kind of touched on it here. There's effective R values. And I think most of what we're looking at in terms of like compliance based modeling isn't really a full understanding of what the effective R value is. We're starting to see that change a little bit more as thermal bridging analyses and thermal bridging factors really get dialed in and understood. And since these buildings were tuned to a specific net annual energy usage, we made sure that we were fairly conservative in our effective R value calculations in terms of really understanding and doing sort of quantitative takeoffs of the blocking and strapping in your walls and understanding how much thermal bridging is really going to be present in the built condition and making sure that our energy models were set up so that we weren't going to get a number in the model that was not going to be reflective of what we were seeing in reality.
So we'll just want to move to questions soon.
Sorry, I can jump through the rest of this.
Some
So yeah. So again, getting back to the key considerations, really air sealing and control of air filtration, is a key factor. Understanding thermal bridging and moisture management. So looking at where dew points fall within the wall, making sure that the assemblies that we're proposing are going to be durable in a long-term manner because we're making sure that moisture is managed throughout the assemblies. And by and large, that's by having fully vapor open walls, which are able to dry to the outside from both sides of the face of sheathing. Another key consideration is why do we always put cooling fins on our building in terms of pre-finished metal flashing? I understand management is a very critical factor in terms of long-term durability, but when traditional metal through wall flashing is as bad as taking 1 inch of insulation out of the wall right back to the sheathing, are you better off taking that space of insulation out and letting things dry and letting things breathe? Or are we better off with metal flashing? The good news is there's other means of flashing that are not reliant on such conductive materials. I think this image here, I'll give credit to Grant from Lightbox, but I think this is one of the clearest illustrations of having all the right intentions. There's continuity of insulation. There's lapping of the seams in the insulation, really making sure that insulation is continuous. Um, but the issue here is there's a capillary break or there's a separation between the strapping and the cladding. So the strapping and the cladding didn't get wet. But unfortunately, the insulation either settled or it was installed tight to the face of the metal flashing below it. And that didn't provide a ventilated cavity and made sure that any moisture that was being wicked out through that wall was unfortunately getting pulled up through capillary action into that mineral fiber. So this section of mineral fiber at the base of the wall really lost its effectiveness. Um, I'll just quickly, sorry, very quickly run through this, but I think the making sure you do mock-ups and establishing a basis of design and a standard of acceptance of key details regarding air sealing is really a critical factor to project success. Um, Both interior and exterior, so primary and secondary air barriers being like the biggest point to hit on in terms of making sure you're getting the full value or the full effectiveness of the wall assembly that you're proposing. I also want to follow up in saying building envelope commissioning and testing and verification of your assemblies is really key. And I can't state how much value clients get from ensuring that they're um, partaking in this process, because for every dollar spent, you're saving so many dollars in terms of future maintenance hassles by ensuring that through air tightness testing you're minimizing any potential leakage points, both moisture or air within the building that are really going to lead to future issues. And with that, thank you. Be happy to take some questions. Sorry for going long on that.
Oh, it's a lot of things that we can talk about when it comes to insulation. Hey, so we're just gonna bring us all in. All right, so a few questions here in the chat. Totally understand if people need to go. But for Andrew, what are the trends on design and using structural insulated sheeting?
Well, we definitely started to see that coming up a little bit more, mostly on the more on the residential side, I find, than the commercial, based on what I've seen in the market. Like, I know even like us, like Owens Corning, we have one in the US right now that potentially will be coming up to the Canada shortly or in the near future. So it's definitely something that we're seeing more, and we're seeing the value of it. I think when the way the building code changed, and as people try to advance through tiers and to try to get that performance level, one of the ways, I mean, originally we thought everybody was just going to go and put all the exterior insulation on, but instead a lot of people are going to a thicker bat, like an R22, R24 bat, and then potentially using that structural insulated sheathing to achieve that extra performance. I hope that answers Chris's question.
Yeah, and Stephen, if you have anything you want to add, feel free to.
No, I mean, I think there's some concerns around structural insulated sheathing and its availability. We know that's rapidly changing, especially when you look at something like a zip sheathing. But even if we were looking at, for example, like when we had started these projects back in 2022, that was not readily available in the market. So I think that's something that we're definitely going to see advancements in. I mean, I've got a lot of other considerations I would say regarding durability and moisture management, where I think a more traditional hybrid wall assembly may actually be more beneficial. But I mean, that's definitely up for debate and open dialogue as we really get a better understanding of the durability and performance of these wall assemblies longer term.
Sounds good. Okay, so for Andrew again, and of course, Stephen, you can weigh in as well. For embodied carbon, what are the gains made in using recycled plastics versus virgin resin in insulation manufacturing?
Well, I mean, I guess if you're using recycled plastics, obviously, you're gonna you're gonna use less fossil fuel, or less of the virgin fossil fuels, which should lead to less greenhouse emissions from your production process, and then in turn should definitely potentially could lead to a little more of a less expensive product as well too. Now, that's not every manufacturer. That's just kind of giving generals right now. It all depends on the manufacturer's process on when they're using those types of products as well too.
Okay.
Or okay, no, none for Steven. He can do the next one. The next one's for him too.
All right, Stephen, great work on the modeling. What are the ways the customer will monitor the building performance while owning the building for verification and optimization? Also, what level of confidence do you have in the numbers, like range of variation?
I'll maybe start with the easy part of this question, which is the confidence in the modeling. I would say that's something that, based on the fact that we've got some on-site verification as these buildings are coming together, of their air tightness values. I think we're going to far exceed the infiltration rates that we set. And as I noted, that's really the single largest impact related to building energy usage is making sure that that air sealing is really looked after. And as I said, in terms of the thermal modeling, we really dove into trying to get a very good and deep understanding on the thermal bridging. Because I think, as I was noting or alluding to, I think that's something that the current energy code really like it kind of glosses over. Like you're getting effective values that they're looking at framing factors, but like they're not really looking at um, all the different fasteners coming through the system. They're not looking at like linear thermal bridges, like I was alluding to with that through wall metal flashing. Like if you've got one of those every 10 feet up the side of a building to flash out that wall assembly, you've got a huge discontinuity in your insulation and a huge thermal break every uh, every so often, but that runs around the full perimeter of the building. So we did what we could to really try to understand and quantify the impacts of any of those moves and do what we can from a design side to really alleviate any of that thermal bridging in the first place and make sure that there was continuity of both the air sealing membranes, both primary and secondary air barriers, as well as continuity of the insulation, trying to reduce as much of the thermal bridging as we can. So I think in doing so and understanding the what we did on the back end to try to make sure our estimates were quite conservative and again kind of risk averse. I feel like we should be pretty good in terms of net annual energy usage, probably being better in the real world than what we had modeled. As far as verification goes, this unfortunately is a little bit more of a challenge because it's not centralized energy sources for the whole project. Since these are apartments, the sort of development agency in this case had a stipulation that each suite needed to account for its own heating and cooling. It needed to account for its own water usage. So, as much as we'll have an annual understanding of that energy usage, it's going to be a little bit skewed in the sense that every different tenant may operate that space slightly differently. So I think we'll be able to gain a pretty good understanding of how the net annual energy usage really reflects. But I think in terms of granularity, there's so many more things we could have done, and I would have loved to like embed sensors in the walls, get an understanding of like the thermal gradation, understanding of the thermal performance on the wall assemblies facing different directions at different times of the year. And well, hey, by tuning the amount of insulation you need, should we actually be reducing some of the amount on the south side because we understand the annual amount of solar exposure there is there, like, and it's a lot of considerations that I would have loved to have monitored in terms of building performance in the real world. It's just um, it's really hard to get that into a building that is being implemented, especially on such an aggressive timeline. Like we're rolling out like 42 of these buildings over like 24 months. So it's um, as I was saying, it's kind of a bit of a problem of scalability. But again, the really good news is the fact that the client that we're working with is very understanding and responsive to what we've learned throughout the process and how that really drives the development of the future projects with them. Hopefully that answers that question.
Yeah, I think so. Unless you guys have any final thoughts, we're gonna call it a day.
Fill the
Yeah.
envelope first. That's all. Like what Steve was saying. The envelope first. Not everybody thinks that way, but I'm hoping we start looking at it that way. So
I think the key takeaway from my standpoint is again, model early, model often, and really try to have a quantitative analysis, not just a bit of a gut check on the assemblies that we're putting out into the world, and trying to gain a true grasp of their performance.